How Elements Arrived in the Solar System by Charisma Burrows and Isabella Granis.
Fusion, nuclear burning. It's the process of smaller atoms, as in hydrogen, creating larger atoms, which ergo is helium. The stars keep forming bigger and bigger atoms once they run out of hydrogen, meaning that all the helium they've made from their hydrogen will now bond with each other. When atoms connect, they release energy, so the sun and stars are constantly producing energy. So constant energy is coming from the center of the star, but the gravity of the mass in the center pulls it back in. When our personal sun formed, the one that always gets in your eyes, the remaining dust and gas collapsed into a disk in the solar nebula, causing the start of our planet's formations.
Fusion in the star cycle. Stars are under incredible amounts of pressure from the beginning of their life cycles to the end, but fusion is not observed until the main sequence stage, which follows the protostar stage. The protostar stage occurs after the solar nursery. If the cycle continues to the red giant stage after the main sequence, the star will begin to lose energy and condense after most of its hydrogen has been fused. These stars will eventually shut down completely into black dwarfs, a star form completely devoid of energy. If the star's mass is large enough, it will propel into a more violent reactive cycle that will lead to the creation of all periodic elements. We will talk about this later.
Nucleosynthesis, where the lighter nuclei, as in elements, combine to form heavier nuclei, as in helium, to all the other elements until iron, which we'll talk about later, requires a high-speed collision, which requires high temperatures, 5 million degrees Celsius at least. Talk about a sunburn. Elements with more protons require even higher temperatures, and our sun is currently fusing hydrogen to helium. So, in this diagram of the hydrogen to helium fusion, you see how the pressure from the energy created is moving outwards, but the gravity pulls it back in. Fission. It's caused by the binding energy curve, where fusion turns to fission, as in pretty much everything after iron. The nuclide 62 nickel is the most tightly bound atom present in fusion, but is not nearly as abundant as iron 56, so that's the one that scientists agreed to use as the binding energy curve marker. The neutron flux is present in a massive star. Heavier isotopes are produced by neutron capture. Isotopes are unstable, so there is a dynamic balance to determine whether any net gain to mass number occurs, and the heaviest isotopes are formed by a supernova. So, in this example, a neutron goes to the target nucleus, where they're adding to create larger, different elements. So we have extra neutrons and the fission product, which is a different element from the original starting element.
Supergiant stars. If a star's mass reaches 5 times that of our own sun, it will continue to the supergiant stage where rapid, unstable fusion begins. These reactions will yield elements such as beryllium, carbon, oxygen, neon, and magnesium. At 8 million degrees Celsius, supergiants will fuse cobalt, silicon, chromium, nickel, and iron in the core. After the iron core fuses, this process stops. Supernovas. If a supergiant star has enough mass after conversion of elements, it will turn supernova. This phenomenon is an incredible explosion that occurs after the iron core of the star collapses. The energy from this explosion will yield gold, silver, lead, and nearly all of the rest of the elements on the periodic table. A supernova star releases energy equal to that of our own sun's lifetime. Leftover energy from this explosion will return to the solar nursery, where it will fuel the next born star. You can see the cycle in this diagram, which starts at
the nebula, which turns into a protostar, which turns into a main sequence, which is what our sun is. And then you have a giant or supergiant, which is what can happen. Either they are so big that they become a supergiant, or they're not as big and they're a giant and they go off and do their own thing into turning into a dwarf because they're small and they know it. And if you're a supergiant, you turn into a supernova because you just have to do it and you're just like super and everything. And then you will turn into a black hole if you're really, really big, or a neutron star, which is a non-charged star because neutrons have no charge, and that's all it is, because it forces the protons and the electrons together in like a big mash, and then they form neutrons. Condensation. When temperatures are hotter near the center of the proto-sun, as in our sun before it was completely formed, which pushes the lighter elements out, which is how you see elements that are volatile, which tend to be ices and water and ammonia and carbon dioxide and nitrogen, out into the farther planets, where you see refractory elements which have high melting points and are solids such as metals and silicates, and they are in towards where the sun is, such as Earth and Venus. As the cloud around the protosun cooled, the gas temperature dropped below the condensation temperatures of metals in the inner solar system. This results in silicates and rocks near Earth and ice and water by Jupiter, with other volatiles farther out because they're lighter elements. So there tend to be refractory materials closer to the sun, as in Mars, Venus, Earth, and volatiles farther from the sun. Condensation of refractory materials lead to rocky and metallic terrestrial planets, such as Earth. And in this diagram, you can see the heat and the types of elements that go with it. So the closer to the sun you see your harder metals and rocks. When you're in the middle you see water and ice, and once you get farther out you're getting carbon dioxide and nitrogen and all those other fun elements. Gas giants. They're composed of simple compounds that will condense to a solid. The most common compounds are water, ammonia, and methane. The snow line, like a snowball, is the distance beyond which water condenses in clumps, eventually hitting each other and turning into planetesimals, as in like tiny planets. With large volumes of the outer solar system occupied by planetesimals, they accumulate into large planets by constantly colliding, and then they are large enough to hold hydrogen in their center. Since hydrogen is so abundant, they become giant planets. And here we have another diagram showing the frost line, another name for the snow line, and how you have from the protosun out the rocky planetesimals and then the rocky ice planetesimals. So you can see how that line of what freezes and what doesn't freeze changes. When planetesimals were first created, large meteorites and comets were orbiting around the sun. When these collided, they formed larger bodies, resulting in the eventual creation of protoplanets, as in baby planets. As larger planets were created, they had more gravity, resulting in even more planetesimals being pulled in. After the planets formed, planetesimals remained, so there is still a chance of major impact happening to Earth we know nowadays, such as these diagrams colorfully show. The end of times. Comets. A strong wind blew through the remaining gas from the nebula disk out, thus creating the oldest meteorites and comets on the outer layers of our solar system. The comets are composed primarily of water and ice, with significant quantities of trapped or frozen gases like carbon dioxide, the type of volatiles you see farther out from the protosun. Comets are in the outer solar system and get pulled into terrestrial planets by gravity. This results in impacts on planets such as Earth that end up creating our oceans and our atmospheres. And this is the reason we are able to have life, because of these comets that hit our planet. Here we see some fun comets with their tails and their nucleus and comma.
There's a lot of tails.
And that one on the right looks like it's going to hit Earth.
Go back to the slideshow mode. Is it still going?